When you eat a lot of protein, theory is that it all ends up going into making your muscles bigger. But unless you're actually doing something to require your muscles to be bigger, like exercising, lifting weights, something that like stretches your muscles don't need to grow at all. So when you eat that protein, what ends up happening to the protein? So all of the blood that flows from your intestines before it goes into your heart to get circulated throughout the rest of your body, it has to go through your liver. A lot of that is to detoxify stuff, but one of the other things is to let your liver take what it needs before everything else. So about 50 to 60% of the amino acids that you eat most of the time end up staying in your liver and get converted into something else because they don't need to make any type of muscles. The main thing that your liver is using those amino acids or those proteins that are made up of amino acids, it's converting those amino acids into glucose because your body is at all times trying to prepare for when you have no access to food and you still need to make energy. And what is it going to use when you don't have any energy available from food? It's going to use the glucose you've got stored up, or it's going to make more glucose so you can have more glucose stored up for next time if you've gotten access to glucose currently. So your liver is going to make more glucose. How is it going to make more glucose? A process called gluconeogenesis. And the process of gluconeogenesis is covered in one of the videos linked in the description below. Biggest, most important thing to know, at least to get started when it comes to gluconeogenesis, is that you've got to start with pyruvate or oxaloacetate. Most of the time when scientists talk about gluconeogenesis, they talk about it as basically being the reverse of glycolysis, where the steps that happen in glycolysis, the opposite is going to happen in gluconeogenesis, but using the same enzymes in the same process. So the reactants become the products become the reactants. For a lot of the steps, that is the case. So for example, this phosphohexylase isomerase is the same for glycolysis and gluconeogenesis. Same thing with this one. There's a whole lot of these enzymes you'll notice are the same going down as coming up. However, there are two steps that are happening within gluconeogenesis that don't happen within glycolysis. One of them being this fructose 6-bisphosphate to fructose 6-phosphate. It's going to be opposite, like those are not using the same enzyme. But importantly, as it relates to the creation of phosphoenolpyruvate in the first place, this pyruvate kinase to make pyruvate is not going to be used if we're getting rid of pyruvate. Doing gluconeogenesis, this pyruvate has to first become oxaloacetate, which then becomes phosphoenolpyruvate. The enzymes that are used, this pep carboxykinase and the pyruvate carboxylase, are not the same as this enzyme. So these are reactions that happen in one direction. They're not bidirectional. But where does this pyruvate come from in the first place if we're trying to get to this oxaloacetate? Before we talk about how these reactions occur in the first place, let's talk about the structure of pyruvate. You can see here is a molecule. This carbon has a double bonded oxygen as well as an OH group. So because of this, this is a COOH, which is also known as a carboxylic acid. Anytime you have a carboxylic acid, the word is going to end in ic acid. This is going to be called pyruvic acid. However, at physiologic pH, or a pH of about 7.4, the hydrogen that's on this amino group, the hydrogen that's on this carboxylic acid group is going to leave. And so it's actually going to be COO minus group. This is going to be an O negative. This is still going to be the double bonded oxygen. This is still going to be a double bonded oxygen. And that carbon's still going to be there. And so when this becomes a negatively charged molecule, instead of being a COOH to be carboxylic acid, COO minus, this whole group together, it's going to have an ending of 8. So instead of this being pyruvic acid, this is now going to be pyruvate, because that OH has lost its hydrogen, it's just an O-. So in the human body, which does have a pH of about 7.4, you're going to have pyruvate, not pyruvic acid. But recognizing that this does have the carboxylic acid is going to help. So pyruvate is just one of the molecules that you can use to make into this phospholinopyruvate. But if you go back to here, you can also use oxaloacetate. Now, oxaloacetate is similar to pyruvate in that it has that carboxylic acid with the -ate ending. However, oxaloacetate has more carbons added to it. Oxaloacetate looks like this, where you have two carboxylic acid groups on it. You've got one on this side, got a double bonded oxygen just on its own, which makes a ketone. We'll talk about that in a second. But then you've also got this other carboxylic acid group. So same thing's going to happen where this gives you an ic acid ending. The rest of this molecule gives you the oxaloacid, and because their OH is still there, this is going to be oxaloacetic acid. Similar to pyruvate, if you remove this H group, then this molecule is going to be called oxaloacetate. So we still got the double bonded oxygen, COO minus group here. This one is still going to be a COOH group. On the other side, that hydrogen might also lose depending on the situation, but for our understanding of nomenclature purposes, oxaloacid, and then this COO minus gives you an 8 ending, so it's going to be oxaloacetate. In both situations, you've got a carboxylic acid, but the other thing to recognize is that as you go away from the carboxylic acid, you're going to name the carbons alpha, beta, gamma, delta, etc. So this first carbon away from the carboxylic acid is called the alpha carbon. The second one is going to be the beta carbon. Same thing here. This is still the alpha carbon. This is the beta carbon. There's only two other carbons, so it's just alpha and beta. Whereas for oxaloacetic acid, you're going to have this be the alpha carbon, you're going to have a beta carbon, and then you're also going to have a gamma carbon. And that gamma carbon is where the other COOH group is attached. But in either situation, this is again alpha, beta, gamma. In either situation, you'll recognize that this other oxygen, this double bound oxygen, is attached to the alpha carbon in every single situation. And when you have a double bound oxygen in the middle of a chain, a C double bonded to O in the middle of a chain is called a ketone. Where the ketone is attached, it determines. So because on both of these situations it's attached at the alpha carbon, these are called alpha ketones. And they also both have that COOH group, so they both have that carboxylic acid. And so that leads us to this general class group of things where you have a COOH as well as on the alpha carbon, another oxygen double bound to the carbon. These are called alpha ketoacids. And for all molecules that are involved in gluconeogenesis, they all start by creating some kind of alpha ketoacid, whether that's going to be pyruvate here or oxaloacetate here. You have to make an alpha ketoacid.